Thank you very much. So for the people here I haven't met, my name is Robin. I'm from Norway. I do not work with software development. It's more like a hobby thing for me. And on my free time, I've worked with being the maintainer of Elm Community Dict Extra, for those of you who have tried that out. I've also made a new implementation of arrays. So if anyone here have runtime issues with arrays that are currently in Elm core, you can try out this library and it should fix most of your problems. So it shouldn't surprise many of you that the purpose of this talk is related to collections. That's kind of where I spend most of my time. And the goal is to kind of learn you guys how the core collections in Elm are implemented. And by core collections, I'm talking about lists, I'm talking about arrays, dictionaries, and sets. We're going to do this for two reasons. First of all, it's fun. If you're as damaged as me, that is. And it's kind of because immutable collections has certain performance challenges that mutable collections don't have. It's kind of interesting to see how we work around those limitations. But also because if you know how the core collections are implemented, it'll be painfully obvious when a collection is good for any given use case. Or at least that's the hope. But before we begin, just a warning. The implementations you will see, the explanations I will give you, does not necessarily represent the way things currently work in core. It's just, I'm just going to explain things in a way that gives you the rough idea of how things work. So I don't want any questions later on saying that it would be better to implement this way or that way. It's just, they probably are. So we're going to begin with list. List is the most common data structure in Elm. Anyone who's used Elm has used list some way. And a list has a very simple implementation. And if you were to give it like a sum type definition, it would probably look something like this. A list of some value can either be empty or it can be a cons. Cons is just a historical name, but what it means is that it's a value and a pointer to some other list. And that probably doesn't make sense for most of you, so I'm going to give you like a visual walkthrough of how this works. So if you want to represent the empty list, you just represent that by the empty value, essentially. That's not a big surprise. But if you want to represent a list with a single value, like 3, for instance, you would do it by creating a cons of 3 pointing to the empty list. If you want a list containing the values 2 and 3, create a cons of 2 and point that to the list containing 3. And again, list 1, 2, 3, cons of 1, pointing that to the box of 2 and 3. But of course, the only thing you pass around your code is this single box. And when you add something to a list, you only add a single box. So adding stuff to a list is very fast, extremely fast. There's probably not any way you can do this faster than this implementation. But since you are just passing around the first box, you essentially only have reference to the first element. So if you want to get to the end, you kind of have to iterate through all these boxes until you hit the end. And that's going to be slow. So if you have a list of 1,000 elements, you're going to have to dig through 1,000 elements to reach the end. And that is going to be slow, or slower than many other lists. There's another interesting problem with lists, and that is like if we are going to implement a naive map function for this, and for simplicity, we're just going to pass like map identity and see how this goes in the naive case. So we're going to start with an empty list, and then we're going to begin with the first element, pass it through the identity function, and add that to the empty list. And we're going to do this for the second element and the third element. And then we're done. And you're going to see that, like, but just providing a naive implementation, like the simplest implementation we can think of, we, as a side effect, reverse the list. So to kind of like have a map function that doesn't reverse the original contents, you're going to need to handle that somehow. And that is going to be like that. Essentially, you're iterating over the list twice in some way, and that is going to affect performance. So just to summarize lists, they are very ideal. They're great when operating at the beginning of the list, because that's the pointer you're sending around, so that's going to be constant access, whether you're removing, adding, or altering the first element. They're going to be great when you're iterating from left to right, because that's how you navigate through the list anyway. And they're very good when you only add stuff to a list. You don't care if there are values in there that are equal already. You don't care if they're added to the front or the beginning or whatever. You just want to add something to a collection. In those cases, lists are great because adding stuff to a list is fast. But for everything else, list is kind of not great. That doesn't mean that you should never use it if you have a suboptimal case. It just means that list is not like good at these cases. The normal thing to talk about after a list would be arrays, but arrays are kind of complicated. They're easier to explain if I go through the dict implementation first, so that's what I'm going to do. So a dictionary is a type, it's essentially the programming version of a phone book, right? You have a name, you want to look up some other value associated with that name. And you would probably end up with something like this if you were to implement it yourself. Again, this is not the definition you will find in Elm Core, but it's enough to give you a rough impression of how it works. So you would have a type dict with a comparable key. Why you need a comparable key, I'll go through in a moment, and some value. And every node in this dictionary can either be empty, or it can be an actual node with a key, value, and 2 references to other nodes. For simplicity, I'm going to call these the left and the right nodes. And again, visual representation. So luckily for us, Fruit.com is going to need a shopping cart. And we have decided to implement this as a dictionary. So in the beginning, the shopping cart is empty. There is nothing to see. And then the user wants to add bananas to his list. I'm going to add 5 of those. There are currently no left and right references left yet. Sorry. So those are just empty as well. But then we're going to add apples to this list. Now, A comes before B in the alphabet. So apples is going to be a less than or a left reference. It goes on the left in this dictionary. If you want to add like oranges, O comes after B in the alphabet, so this is a greater than or a right reference. And then if you want to add something like mangoes, M comes after B, but it comes before O, so it goes there. And that's essentially how dictionaries work. This is why you need comparable keys, because that's how you navigate through this data structure. Retrieving something from a dict is very great, because every time you do a comparison, like if you want to find out where mangoes is, you know you need to go right, which means you don't need to consider anything on the left. So if you have 100 values on the left, you just don't care about those. You just navigate your way through. If you want to alter apples to say 3 instead of 2, that's also very good. You need to copy bananas because you're changing a reference there. And you alter apples to say 3, but you don't care about the other 2. You just copy those. And that's kind of like how you have fast, immutable modification of this thing. So it's very good for that. But there is one problem with dictionaries, and that is, let's say currently the user added things in a very optimal order, right? It added things in an order which gave you a very nice tree representation. But what if instead the user added things in alphabetical order, like this? This is a list, right? This is a linked list. You have one reference, and to get to the other, you need to go all the way. So dicts need some way of transforming this into this, because this is the optimal representation. This is what gives you the characteristics that you need. And so the implementation in Elm and many other implementations has some way of balancing itself. And that, of course, affects insertion time. So to summarize, a dict gives you quick access by key. It gives you a binary search. You can't have duplicate keys in this, because the only way you know that you have a key in the dictionary is if you're comparing them to be equal. So you can't have comparable keys unless you, of course, store your values as lists to begin with. And as a result, all the keys are in sorted order. So if anyone wondered why fold left or something would go through keys in alphabetical order or numerical order, it's because of the way you arrange things. And yeah, it requires comparable keys. In Elm, in contrast to many other languages, you can't extend the definition of comparable. So this actually becomes a limitation. Now, personally, I never needed dictionaries for anything other than numbers or strings myself. But for some people, this might be a problem. Probably why Haskell people like type classes or something. The next data structure I'm going to go through is sets. Sets are very similar to dictionaries, but they are, or not really. But they, like, a set is essentially like a list of elements in no specific order. And the guarantee you have is that you have no duplicate values. You can't have a set containing 2 strings of Robin, for instance. That's not possible. You can have maximum 1 string there with the value Robin. And a very simple way to get a data structure like this is by just saying that set is a dictionary where the key and value are the exact same type. the exact same thing. And that's essentially how it's implemented in Elm as well, which gives you, the implementation is more or less the same. It works pretty closely to dictionary, although the use cases are pretty different, right? You use a set to figure out, like, is this string in the set or not? You don't use it to, okay, I have a string, give me something else. So the use case is different, but the actual implementations are pretty similar. Downside of a set is that suddenly your values need to be comparable as well, which greatly reduces what you can use sets for. And then we come to arrays. Arrays are very interesting because arrays' main use case is that you can get one value from anywhere in the array with the same performance as you would get like the first element, right? A list, in contrast, is very fast when you want the first element. It's very slow if you want the last element of a list. An array has equal performance no matter what value you're looking for. And the only way we can actually have something like this in JavaScript is either to use an object, but objects doesn't work great because you need a way to add stuff to this. Or you can use just a normal JavaScript array. And if you were to create an immutable version of that, you could just like say you're not allowed to call things on the JavaScript array directly, but instead create your own API. And so when we modify the array, we make a copy, we modify that copy, and return that for every operation you make. But this is going to be like naive, that's going to be a naive implementation because as this array grows, you're going to need to copy more and more elements to modify it. And so when you get up to like maybe, I don't know, like 20 elements, modifying array is only going to be pretty slow compared to a list or a dictionary or something like that. So what we do is that we take the naive implementation of an array and we borrow a trick from the dictionary implementation. We're essentially saying that like dictionary has two ways to go from a given node, like either left or right. You can go two ways. But in an array, what we do is that we say that, okay, instead of left or right, you can go from 0 to 7. I picked, like that's a branch factor of 8. I picked 8 for this talk because it's easy to fit on the slide. The actual number in reality could be something else based on benchmarking. It's 32 in the actual implementation, but that doesn't fit as well on the slide. So what you do when you reach a branching factor of 8 is that you start to make a tree out of it. Right? You just say that, okay, I'm going to create a new node above this, and it's going to point to this one. And then if I want to add more to it, I just create another tree pointing to the next array. And that way, when you add stuff to this, you don't need to modify the entire thing. You just need to modify like a path through the array. And this will be pretty fast, because if you're modifying an array of like, say, 100 elements, you don't need to copy all 100 elements to make a new immutable version. You just need to copy like the top, which is going to be like, I don't know, maximum 8 references, and then another 8 references, and then you're done. Not good at math, but I think that's how it works. The interesting thing, of course, if you do this, you're going to need some way of navigating this tree, right? You can't compare things and go left and right anymore. You need some other way of navigating. And the way we do that, like if we take, like, because you know that you have an index, and an index of 5 is going to give you the 5th element. This is like a guarantee we have. So is there any other way we can look at an index? Is there a different representation of it we can look at? So if we take some random index, like 143, which is just a random thing, is there any other way we can represent this? And so computers don't actually understand numbers like we do. A computer doesn't understand the number 143. It needs some other way of representing that. And it does so by having a representation like this. 32 bits, right? Zeros and ones. In some given combination, gives you 143. But since we are only storing 8 values in each level of the tree, we don't actually need a 32-bit reference, because that can store numbers from like minus 4 billion to 4 billion, which is a big range for us. So what we do instead is that we divide this 32-bit number into groups of 3, because 3 bits is enough to represent the numbers 0 to 8. So what we do then is that we say that, look, if you're looking for index 143 in this array, and you're at the top level of the tree, you're going to look at the first 3 numbers, and that's going to give you index 7. And if the array is big enough, you're going to find a reference to another level of the tree, And then you're going to look at index 1. And then you look at index 2, and then index 0. And then eventually you will find the value that you're looking for. I hope that made sense. I don't have time to really dig into this. So just to summarize, that's essentially how an array works. What you would use an array for is, of course, to retrieve a value quickly from anywhere in the array. And it's also fast when adding stuff to the end, in contrast to a list, which is fast to adding stuff to the beginning. That is not to say that an array will be fast. It's not as fast to add stuff to an array as it is to add stuff to a list. It's just that array is way slower if you want to insert something which is not at the end of it. You also have fast map, filter, fold left, and fold R. The reason I put this in is because like a list, if you perform a list map operation, you need some way to reverse the result. Right? In a naive case, the result will be reversed, so you need some way of compensating for that. Array doesn't need to do this. So if you try to benchmark this, I did, but I didn't have time to show off here. So if you benchmark this, you would see that arrays are way faster at the map operation than lists. Way faster. Filter is about the same performance, and fold right, of course, is going to be way faster than an array as well, because an array can just start from the right and fold. A list has to find the end first and then fold in the correct order. So I've focused a lot of implementations. When it comes to what you would use the data structures for, you would use a list, like optimally, when you're operating at the head or the beginning of it, or when iterating from elements through left to right. Fold left or filter, yeah, those kind of operations would be good for a list. You would use an array when you need to access one element in there quickly, or when you need to fold in the opposite direction. You would use a dictionary when you need to access elements by key, and those keys aren't necessarily sequential numbers, as the case is for an array. And you use a set when you need to operate with unique values in some way or another. When deciding what collection to use, try to remember that Elm tries to help you in this. Like, there's a reason the list module does not expose a getByIndex function or setByIndex function. It's because lists are not great for those use cases. They're slow for that. You should use an array instead. And you should try to avoid converting between collection types. If you're performing list map, fold left, or something like that, and then convert to an array because you need to get the fifth element, and then convert back to a list, that is going to be slow. So try to pick the data structure that fits most of the things you're trying to use it for. So I hope that was helpful, and I'll take questions if you have them. Thanks.
I want to add a quick note for folks that, interestingly, in the browser, the biggest performance cost is dealing with the DOM. So you want to be very conscious of the scale of the performance cost. So I recently was messing with a benchmarking thing of a bunch of different front-end frameworks, and the implementation, for some reason, it mapped over a list, converted to an array, then updated the array, then converted back to a list. Yeah. And I was like, that surely would be faster if we just did it with the map and didn't do these conversions. And it had no noticeable effect on the overall benchmarks that change was made. So the cost of DOM manipulation can be huge, and that's something to keep in mind, right? So if you say, well, this is definitely going to be better in the asymptotics, but measure it, yeah. And be aware. Like, don't sacrifice too much for what seems to be definitely the right choice. That is
definitely something. So if you are going to decide on the collection, do not decide from a performance perspective, because even if DOM things are most important things, keep in mind that you're creating a single page application. You are not going to have big enough collections probably for it to make a big difference in performance. Only if you have a performance problem should that dominate the collection type you pick. Anyone else?
Thanks. Hi. So I think you said that you have built an alternative array implementation, and I was kind of expecting that to be the punchline of your talk. So did I miss something?
Well, I didn't want to focus on it, but the array implementation that I wrote is already merged in Elm Core. So that'll be in the next version of Elm Core, it's going to be my implementation to use. But if you need to use that implementation now, thanks. But if you need to use that implementation now, you can. And the only thing you need to change is the namespace import.
Is it interestingly different from the one that you just showed us? And if so, can you explain how?
Yeah. So okay. So the implementation we have today is a relaxed radix B tree, and the implementation I have made is a hash array map trie. What that means in practice is that my implementation has a little bit faster insertion times. If you want to replace a value or if you want to add values, my version is faster. But if you want to append or slice, the version in Core today is faster. Of course, the problem with the version of Core today is that it's not necessarily always immutable. So, and you can get runtime exceptions in certain cases. So stability trumps, in my view at least, stability trumps performance for certain things. So those are the differences. Yeah.
So if you have other questions, can you stand up? Yes, please.
Yeah, just a question.
Attends.
Yeah. Why is there even a normal list and like a normal array in Elm? Like I come mostly from Python, and there in the standard library you have different collections, but the normal one is just a list that you can do most of the things, and then so I don't even have to decide what to take. Just normally I take the list. And here I the programs I did, I always had to think, should I take a list, should I take array, why should I take this and that? Do you have like some remarks to that?
Some remarks. So like I tried to touch this briefly when Evan came with his 2 cents. If it's performant enough, then just use a list. Right? If you notice that you have performance problems, then consider an array. If what you need is to get, like if you need index 50, you don't really care about those before, then array is the best pick for that. But if you don't have any performance problems doing that with a list, then just stay with the list, because most things operate on lists anyway, so it's more convenient to use.
Like a magic number, which side?
So an array, for its use case, will always be faster than a list, unless you want the first element. Always. But like, because most things in Elm, like if you want to convert something to a dictionary, it's easier to do it with a list because you have from list to list operations, right? So it's more convenient in general to work with a list. So unless you have performance problems, just stick with that. Yeah.
Okay.
That was it.
So that's it.
Thank
you very much, Robin.